can come in that plan, no? Or you not the camera. So we will start in just few minutes.
Sure.
Okay, Srikanth. So we are just starting, eh?
Yeah, sure, Pankaj.
Tell you few things about our center. Okay.
Oh,
So
yeah.
okay, so I mean Secure, which is Center for Quantum Engineering Research and Education, is one of the centers of TCG Trust. And this center is dedicated to research in the frontiers of quantum science and technology, which includes quantum computing, theory and experiments, quantum technology and sensing theory and experiments, and theoretical aspects of quantum information. So we are here celebrating this, International Year of Quantum Science and Technology. And at Secure, we are organizing a series of colloquiums apart from 4 conferences. We are very happy and privileged to have R. Srikanth as from Pool Pragya Institute of Scientific Research. And I know him for, I think, more than 2 decades. And he is fully dedicated to foundational aspects of science as well as philosophy of science. And as a young, passionate scientist, he wanted to prove when he was young. Okay, so I don't
Okay.
know work in these areas of foundation and as well as philosophical aspects of science. He will tell us about some more mundane things like concatenating and quantum error correction code. So Srikanth, you can.
Yeah. Thank you so much, Pankaj and Professor Bhanudas, for this kind invitation to your esteemed institution, which it's a pleasure to be here. Am I audible? Am I audible?
Yes, yes, you are.
Oh, okay. Oh, yeah. Thank you. So I'll be talking about this work, concatenating decoherence-free subspaces and quantum error correcting codes. This is based on a work with Mr. Nihar Ranjan Dash, Mr. Sanjay Datta, uh, students at IIT Jodhpur and Purna Pragya Institute, and Professor Shubhashish Banerjee. That was published last year. So the outline of the talks is an introduction, and people here would be familiar with quantum error correcting codes, but I'll introduce DFS, that is decoherence-free subspaces, and how the idea of code concatenation and applying code concatenation to DFS in QECC, and 2 example schemes to illustrate the ideas, followed by a conclusion. Now, as we know, owing to environmental interactions, errors due to decoherence arise, reducing the fidelity and reliability of quantum states and operations. So, we have quantum error correcting codes, decoherence free subspaces, or dynamic decoupling as some of the methods that are employed to protect quantum information. Here, quantum error correcting codes are active methods for fighting independent errors. Usually, quite generally, you can fight independent errors, and it requires an active method in the sense that we identify and eliminate the error. By contrast, DFS, the decoherence free subspaces, are a passive method of fighting correlated errors in which we encode quantum information in noiseless subspaces, that is, subspaces rendered noiseless thanks to symmetries of the dynamics. And concatenation is something that we use to combine simpler codes to form a robust long length code with exponentially improved error correcting rates, but at the same time, the decoding difficulty will not scale exponentially but only polynomially. So in concatenation, we encode an inner code into an outer code. So we first code with the outer code, and in each blocks of the outer code are specific qubits of the outer code we encode within inner code, and we can iterate this to multiple levels. Now, one can concatenate, for example, dynamic decoupling with quantum error correction, or DD with DFS, or quantum error correcting codes with quantum codes with DFS, which have been studied by various authors. Specifically, concatenating DFS and QECC, which is what we study now, gives protection against a combination of correlated and independent errors. Yeah, and concatenation is something, for example, that the quantum computing threshold theorem for fault tolerant quantum computing, which assures us that we can indeed perform, reliable quantum computing. It rests on the concept of concatenation. So all our IBM and all these quantum computers must do use concatenation extensively. Now, by way of a brief introduction to this area, decoherence-free subspace is a Hilbert subspace that is invariant under non-unitary dynamics. It's like a quiet corner. So you have a rough sea, but you have a rock. So you can take shelter behind the rock where it is quiet. So it's a quiet corner in the same way in Hilbert space where the system is decoupled from the environment and thus subject only to unitary evolution. So when you correct information in a DFS, you at most apply a fixed unitary operator. Now, DFS can be represented as one can also represent it as a kind of an error correcting code that are passive error correcting codes, and that information is encoded in them, and then they don't require active stabilization in the sense of identifying and eliminating those errors. Instead, fixed unitary recovery operators will be enough for us. And in terms of the Hamiltonian, you have the system Bath Hamiltonian. So, as we know, it's the standard formalism. You have the system Hamiltonian plus Bath Hamiltonian. And then you have an interaction, which again in the standard way is written in terms of the sums of products. Now, the DFS is a subspace spanned by these states phi, provided it is an eigenstate of all these SI operators which act on the system Hilbert space. And furthermore, we assume that the system and path start in a product state, and then there is no leakage of states. The system Hamiltonian acting on any of these states should not push it outside the protected or the DFS space. If these three conditions are satisfied, then it can be shown that you can create this quiet corner which is decoupled from the environment. And there's yet another useful way to look at it. So you can look at it in terms of the Krauss operator formalism, where we have put it in a diagonal form. And so you can think of the full Hilbert space of the system as a tensor sum of the DFS space and the space that's its complement, orthogonal complement. And in the DFS part, you have this unitary that acts on it, whereas the matrix AJ, which acts on the other part, could be an arbitrary noisy matrix. But the part which is acting in the DFS would be a unitary operator. So in other words, any information that you encode in it stays put except for a fixed unitary operator. Now, because of this, the DFS is obtained by now the code for the DFS in terms of an error correcting code, which is the result we need for performing concatenation. From the considering the irreducible representations of the Krauss operator of the collective decoherence, we can obtain it. Consider, for example, a noise which has Krauss operators which are identity. So we have a 2-qubit system which has an interaction Hamiltonian, and the Krauss operators are described by, the operator sum representation requires 2 Krauss operators, which because of the symmetry, they have this group structure. And it has 2 irreducible representations, that is 1, 1 and 1, minus 1. Now from these representations, one can construct the projectors to the DFS code space. Let's say, for example, we take it to be 1, 1. Then correspondingly, we have P plus, which is equal to half II plus XX. So this would be the projector to a particular choice of the decoherence-free subspace. Now, this is spanned, for example, by the states in equation 2.3. You can see the first row, which is gamma plus. So you have these two states, barring a normalization factor 0, 0 plus 1, 1, or 0, 1 plus 1, 0. So you can see that if you apply II or XX, the this particular subspace remains invariant, which is indeed the property of a DFS. Therefore, as given in equation 2.4, I can have 0, 0 plus 1, 1 identified as the logical 0 state, and 0, 1 plus 1, 0 given as the logical 1 state. So with this explicit, code like where we have given it the form of an error correcting code, we can concatenate DFS and QECC. Now, previous works have considered QECC as an outer code and DFS as an inner code, which was done by Lidar way back, or vice versa by Cafaro in two papers. Here, what we do is we consider both of them in the same framework and also compare their properties in terms of entanglement fidelity or the pseudo threshold in terms of study the performance of both these types of orderings. A very brief introduction to quantum error correcting codes is that you have an NK error correcting code. It encodes k logical qubits.
Thank you.
Yeah.
Certainly.
Into n physical qubits. For example, you have a bit flip code. That is, you have a bit flip and you have a 3-qubit bit flip code which can correct a single bit flip error. In this, the logical states are 0, 0, 0 and 1, 1, 1. This is familiar to us, and these two states are stabilized by these operators ZZI and ZIZ. That is, applying these operators, you have a +1 eigenstate that's obtained. And the encoded not state is given by XXX. That is, applying it to 0, we get a 1, and from 1 to 0. A slightly more complex example would be the Knull-Laflamme phi1 quantum code, which is the smallest code that corrects arbitrary single qubit errors, and it's defined by the stabilizer group, which is given by this. So you have phi minus 1, which is 4, and hence you should have 4 stabilizers, with the two Pauli operators being given by the logical operations given by this, 5 copies of X and then 5 copies of Z. So of the encoded states, these would behave like a qubit, like a Pauli X and Z operator. Now consider two quantum codes. They could be QECCs, quantum codes, or they could be decoherence-free subspaces, or both. So we have an outer code described by the parameters NO, KO, and an inner code described by NI, KI. Now we want to concatenate it. Now there are two possibilities that we need to keep in mind. One is that the inner code rate divides the outer code length. In this case, then what happens is one can divide NO by KI and one obtains that many blocks into which the inner code can be applied. As a result, the concatenated code would have the parameters NO, NI by KI, KO. So KO is the outer code rate anyway, that remains the same. But the block coding could be affected by whether it divides or not. And if it doesn't divide, then for the outer code, we simply create KI copies of the outer code, and then we have blocks of KI, which are then, when you apply the inner code, they become NI, and therefore you have an NO, NI, KO, KI code. So these would be the parameters that describe the concatenated code. As mentioned before, previous work have considered specific orderings, that is, where DFS is the inner code and QECC is the outer code, or DFS being the outer code and QECC being the inner code. We consider both orderings and compare their error correction performance to consider different situations in which one would be better than the other and so on. And we will consider for this purpose a hybrid independent correlated error model. So in this error model, you would have both independent and also correlated errors, where correlation across qubits is allowed within blocks of our encoding, but code blocks, but not across them. Here's a simple situation. If you have an array of qubits in a quantum computer, along the horizontal line, for example, you could have correlated inform. You could have correlations, but they could be independent in the vertical line. So one way is that we can use a concatenated code where a DFS is used for the horizontal qubits, for coding them along the horizontal qubits, and concatenate it with a QECC which is applied along the vertical direction. So this would be a, a simple arrangement in which such a concatenation would be useful. And the particular noise model that we want to consider is a single qubit error, in which, but they're not independent errors, but there is some correlation. So the probability that there is no error is given by p naught, which is 1 minus p, and the probability that a single error happens is p. And within each block, the conditional probabilities which describe the correlation is described by the simple parameter mu. Now, the failure probability of a code is the probability that an uncorrectable error occurs. In other words, for example, let's say we take a bit flip code. This happens with probability that, as I said, the bit flip code can correct a single error. Therefore, if you have 2 or 3 errors happening, which would happen with this probability, then you will decode the wrong letter than the one that you input. So you input, it's like you input a probability P and you have an output, the failure probability is PF. So ideally, your encoding is useful to you if PF is less than P. And alternatively, we can take the measure 1 minus PF for the concatenated code, or indeed for any code. And this is called the entanglement fidelity. So when you have a multi-level concatenation, it is not hard to see that. So we take one code. So we have, let us say, t plus 1 code. So you have the tth code being the inmost code and the 0th code being the outermost code. And we can recursively encode each of them. So at the inmost level, you have the parameters where that is where you have the physical qubits. So we've introduced the parameter mu because that's where the correlations take place. After that, you just have block versus blocks of coding. So you first apply that code, and then each code or each block, certain blocks of the inner code are encoded with the next layer of outer code, and then the qubits of that code are again and you proceed in that way. So if the first one has the probability which is mu comma p, then this is fed in as the input probability to the next layer, and this way we proceed recursively to get the final failure probability of the concatenated code. So as you can see, each level lowers the input error from the next layer. So when I input into a qubit, like I said, if I'm below a certain threshold, then the probability with which it fails will be lower than the input probability. Now, if I keep recursively coding, and then with the addition of each layer, I keep continuously lowering the error rate that we encounter. Therefore, a concatenated code will fail only if failure happens at all the levels. So that is the reason concatenation gives you more reliability. So an easy illustration of this is given in this figure where you have P, and we have taken a code which is a particular code that will be described later on, which is the 61DQ code. And so we have different layers of concatenation. And so as you can see at L equal to 1, we have the outermost, which we see is the one that is the least convex line, which is the plot which describes its performance. With each level of concatenation, we see that the errors are suppressed more and more. But the final threshold where the code fails is of course the same, because when one code fails, then it precipitates the failure in all the upper layers. So the pseudo threshold is basically the maximum error P that we can sustain. That is, if your the error on the physical qubit exceeds P, then the TF becomes larger than P, making it useless to encode. Now we will briefly indicate the following result that when you concatenate the QECC and the DFS code, what you obtain is a degenerate code that splits into actively and passively correcting parts, with the degeneracy impacting either part and leading to degenerate errors as well as degenerate stabilizers. So as we know, DFS is inherently degenerate because you have, in the particular example I showed, II and XX. It is a degenerate error in the sense that you just have a trivial outcome. That is, you have a null outcome in terms of the error that has happened. So you have two indistinguishable errors, and the stabilizers for the DFS are the error operators themselves, meaning that when you have encoded it into the DFS space, applying those operators will reproduce the states that you have. So this degeneracy will percolate, or it will get propagated into the concatenated code, and that is the structure that we want to look at. Now, if you look at the total number of errors when you concatenate a DFS and a QECC, more generally when you have an inner code and an outer code, right, the total errors that you would have basically is, in the case that Ki divides NO, then you would have N0 by Ki blocks, and we would have an inner code inserted for each of these, giving an error EI. So you would have EI into N0 by Ki that comes from the inner code, and you have EO as the number of errors that come from the outer code. And in case it does not divide, by the same reasoning, from the inner code we have EI, and now you have NO blocks, because the outer code, as we earlier mentioned, when Ki does not divide NO, you just make Ki copies of the outer code before applying the inner code. So you have NO blocks. So you have EI power NO, but on the other hand, because you have Ki blocks of the outer code, you have EO power Ki. So this would be a general result, irrespective of whether it's a DFS or QECC. These particular numbers don't matter at this point. I mean the so I mean. But the main thing that I wanted to stress here is that when you have a QD ordering, that is, your Q is the outer code and D is your inner code, then the red part, so the outer code, which is QECC, becomes non-degenerate, and the blue part gives you the degenerate contribution. In other words, you will have an equivalence class of errors in which you have EO sets in which there are EI power NO by KI degenerate elements. And on the other hand, when you have a DQ ordering, that is, you have a decoherence free subspace in the outer part and your inner code is your QECC, then the degenerate, the red part becomes the degenerate one, because in this case you have the EO, that is the outer code being the degenerate code, and therefore you associate the degeneracy with the red part. So what happens is that in the examples we consider, we will actually find it turns out to be just a coincidence that you have, uh, whether we consider the DQ scheme or the QD scheme, that is, whether QECC is the outer code or whether the DFS is the outer code. In both the cases, we'll find that there are equal number of errors, but the partitioning of the sets into degenerate elements, they will become different because of this particular result. If it seems a bit abstract, the examples will clarify it for you. Now, let's say, just to make it concrete, consider concatenation of a 3-1 qubit code and a 2-1 DFS, the two examples that we already introduced. They're quite simple, and at the same time, they bring out the particular structures that we want to illustrate. Now, if we look at a QD scheme, So the outer code is QECC. So we write as an equation 6.1 0 0 0, but each of the zero is then recursively encoded with the 0 0 1 plus 1 1, which is the DFS state. So the zero state ultimately of the concatenated code has these two structures that we've given in equation 6.1. Graphically, we can write it like this. So you have on the top, you have a single node at the top, which is the qubit, and then the outer code is applied, which is a QECC, and then each element of the QECC is then encoded into two of the DFS qubits. So this is what we get. On the other hand, for example, if we have a DQ code, then the zero state would, in the first layer of encoding, as we see in equation 6.2, the zero state would be written as 0, 0 plus 1, 1. And then the zero would then be encoded using the QECC, giving us the state which we've given. So similarly for the one state. So with these, so as you can see, the QD and DQ states will have different code words, which is not surprising. And in this case, a graphic way to illustrate it is that you have this initial qubit at the apex, and you encode it into these two qubits of the DFS code, and then each of these qubits is then recursively encoded into a QECC code. Now the QD and DQ codes inherit passivity and degeneracy from the errors of the DFS. Now, if you look at the errors that are protected at the outer layer, so if we talk about a QD code in the first instance, then as we know, the errors that bit flip code, which has 3 qubits, can protect are the codes that we've written in equation 6.3, namely that you have no errors or you have an error in the first or the second or the third qubit. On the other hand, the operators for ID, the logical operators the for the DFS, which would be ID, XD, YD, and ZD. And because ID, the identity operation, consists of a multiplicity of two, that is II and XX. And one finds that the same multiplicity passes on to YD, XD, and ZD. That is to say, when you have an encoded word in a DFS and you want to perform a logical Y operation on it or a logical X operation on it, there are two ways to do it. If you want to do a logical X operation, you can apply XI or IX. Therefore, each of the letters that you see in equation 6.3, so these are the errors in the outer code, and then the ID would correspond to two codes, or two errors, right? Which is II and XX given in equation 64. And therefore, each of those errors would correspond to two errors. So we can see that we have these 4 non-degenerate errors corresponding to 8 degenerate elements, which is what we have written here. So the first one which we have given is the passively correctable errors, meaning to say that when those errors happen, actually they don't affect the state itself. And the other errors, we will obtain a syndrome in the outer layer. That is, the inner layer is a DFS. So we have 32 errors in all. So we have 4 of these non-degenerate sets, each containing 8 degenerate elements. One can repeat the same exercise for the DQ code. So in this case, the outer layer, you would have II and XX as the two correctable errors, and which are obviously degenerate. And IQ would correspond, for example, given in equation 6.7, into all these errors. IQ into IQ would correspond to all these errors. That is, these are all errors which are correctable. So they be you correct at the inner layer, and then they move on as an identity operation to the outer layer. On the other hand, the X operation would correspond to the four operations that are given in equation 6.8. Therefore, again, counting all these operations, we obtain the following set of errors. But again, we find that you have 32 errors. For example, the blue set again is indicated as the passive errors. That is, you can have these errors happening to the system and they don't affect the system at all. In all the rest, you would need you need to do active error correction at the inner layer, that is the Q layer, and you have all these errors. So now in this case, you have 16 sets of 16 non-degenerate sets containing two degenerate errors. Now, in trying to assess the performance of this, we know that the Hamming bound of a non-degenerate QECC requires that n minus k should be greater than or equal to log 2 of the number of correctable errors. Essentially, this sort of it ensures that you have enough syndromes corresponding to all the errors that appear in the code. Now, we can define something called the Hamming efficiency, which is just this quantity, which is inspired by the Hamming bound. Now, in each of these codes, we know that the number of errors is 32. And when we apply this formula, we actually obtain the Hamming efficiency to be 1. Now, the Hamming efficiency 1 is typical of a perfect code. But in this case, as we saw, it's not a perfect code. A perfect code would, I mean, ideally we think of it as a non-degenerate code in which all of the, I mean, you saturate the Hamming bound actually. So here we do saturate the Hamming bound, but it is because the code, I mean, the non-degeneracy has been used to inflate the performance of the code. So it seems that in the presence of degeneracy, we may generalize the Hamming efficiency to what we call is the modified Hamming efficiency, which instead of just counting the total number of errors, we will look at the non-degenerate sets within each of these degeneracy equivalence classes that we talked about. So, for example, in the QD case, we saw that there were 4 non-degenerate sets with 8 degenerate errors. So, instead of 32, we will just count 4. And in the second case, it will just be 16. And plugging this into formula 6.1, we get numbers which seem more realistic. Saying, and so this would be one way to assess the performance of these codes in terms of how efficiently they make use of all the syndrome space available in order to correct the errors. Now, the exercise of the previous section can also be repeated for the Knill-Laflamme code being concatenated with the DFS. So when you have a QD code configuration, then you have a single qubit. You first encode it into 5 qubits of the Knill-Laflamme code, and then each of these qubits are again encoded into 2 qubit. Each qubit here is encoded into 2 qubits, giving you this particular 10-1 code. So totally you will have 10 these things, and the rate still remains 1, which is inherited from the outer code. On the contrary, a DQ code, you will first encode it into 2 of these qubits, and then each of these qubits will be encoded into 5 qubits. And in this case, in the QD case, we can similarly we can repeat that exercise. Now we have the 16 errors of the Knill-Laflamme code, which we have written out, but we put it in square brackets to indicate that in the DFS, each of these operators will have 2, if you like, interpretations. So for example, an I that appears in 6.12 in one place can be II, or it can be XX, as we've written in the paragraph below. So when you have, so what each of these square brackets indicates is that you actually have a 10, an operator with 10 qubits, actually, with each of the positions here replaced by 2 qubits. So for example, the square bracket, which is given as I would be what we've written in the last line as II comma x6 tensor product, tensor power 5. So you would have those many operators that 2 power 5 operators that 32 operators that stand for each of these. So you have in all 16 into 32 operators, which is 512 elements. So you have these 16 non-degenerate sets, each containing 32 degenerate elements, giving you 512 in all. And similarly, for the you can repeat this exercise for the DQ code, and for which we had given the code configuration earlier. And in this case, again, we will find that we have uh, 512 codes, but in the totally 512 number of errors. But the way it again partitions is that you have 256 non-degenerate sets, each containing 2 degenerate elements. So the partitioning will be different. And I just want to tell you that it is indeed a particular coincidence, or because of the way that E1 and E2, the number of errors are there in the E1 and E2 code and their lengths, that the DQ and the QD yield the same number of errors. This is not generally true. And in this case, we find that the Hamming efficiency is again 1. But if we consider the modified Hamming efficiency, then obviously it is less than 1, which is 8 by 9. Now, ultimately, we are concatenating a DFS and a QKD in order to apply them to situations where you have a mixture of correlated and discrete errors. And in this case, we assume that we have prior knowledge of the value of mu and p in these codes, because if you know that mu is large, then we would want to apply the inner code should be the DFS, because it is more amenable, it is more convenient to apply it to a correlated error situation. Whereas if our model indicates that there are a lot of independent errors, then it is better to have the QECC in the outer code. Now we can now calculate for the 3.1 code and the 2.1 DFS by applying a straightforward Bayesian analysis. We find in terms of P's and Mu's what the failure probability is, as given in equation 6.13. Now we can compose them as indicated in theorem 1 that we discussed. We can compose them to find out the functions for the 6.1 QD and 6.1 DQ. Now this we have plotted here. It gives rise to a sort of a very long expression, which doesn't matter. So to plot them, and then we find that there's some interesting behavior. Now we find that for sufficiently low correlation, the DQ code outperforms the QD code. That is, if you have low correlation, that is largely the errors are independent, then the inner code should be the Q code. So a DQ code helps. And vice versa, if you have a large amount of correlation, then the inner code should be the DFS and you should have a QD code. So for example, as you can see from these plots, if we put mu equal to 0, then we, yeah, so you can find the mu equal to 0, which is this particular code that has come here. So the DQ code outperforms the QD code, as we would expect. And on the other hand, if the correlations are very large, then we find that the DQ code is worse off than the QD code. Actually, the QD code does superbly well. Now, the fact is that if you, let's say you have mu is equal to 0.75, we see that actually the plot, so on the y-axis, we've got entanglement fidelity, and then we've got the probability here. So we see that on this plot, it is convex. meaning to say that it is of no use encoding. When you have a high correlation, using a DQ code, we are worse off encoding than not encoding. So we might as well not encode. And we find a similar behavior also in the second figure that we see, that when you have large mu, that is a large component of correlated noise and with the independent perturbations in it, then the inner code should be the DFS. So that is a QD code. Whereas if mu is close to zero and the independent component of the errors are there, then the inner code should be a QECC, and so you should have a DQ code. Earlier, we talked about how we've looked at how when concatenating them, we also combine the errors of these two qubits. And because of the DFS, the concatenated code also inherits the, the passivity and also the degeneracy that is inherently present in a DFS. Now, as we said, in a DFS, the error operators are also the stabilizers, which are again degenerate in the following sense. What I mean by saying that a stabilizer is degenerate is that when you apply it to all errors they generate, they produce the same syndrome. So it makes no difference. Whereas a degenerate error, so it's this definition is symmetric to what we talk about as a degenerate error. A degenerate error is with respect to all stabilizers, they produce the same syndrome. Two degenerate errors is with respect to all errors, they with respect to all errors, they produce the same syndrome. That is, for any error you take, the syndrome that is generated by stabilizer 1 and stabilizer 2 would be the same. Now, if you look at the stabilizer generators for the 3-1 code, as we know, it is the bit flip code. And, yeah, so this code we have Z1 and Z2 and Z1 and Z3. And for the stabilizer generators for the DFS would be X1 and X2. So in this case, so in the QD case, we can label the qubits. So our outer code is Q. So we have these 3 qubits, and each of them now is split into blocks of 2 qubits each, corresponding to the DFS. And so we can call them as 1A, 1B, 2A, 2B, and 3A, 3B. Now, corresponding to each of these blocks, we have the DFS, right? And the inner code will have these generators, which is X1A, X1B, which is just applying the DFS stabilizer to the first block, to the second block, and to the third block. This gives us the inner code part. For the outer code, we have Z1 and Z2 and Z1 and Z3. But recollect that Z1 has two realizations, that is IZ and ZI. Likewise, Z2 also will have IZ and ZI applied to these blocks. And as a result, you have multiplicity. So if you look at the S4 generator, you have this multiplicity, that is S4 or S5 represent 4 degenerate stabilizers, and each of these stabilizers will produce the same syndrome basically. And only in the outer code will they generate a syndrome. In the inner part, they remain as DFS. So only the outer code determines the syndrome, and therefore these are the degenerate operators, stabilizer operators. Symmetrically, one can also consider the DQ case. So the outer code gives you these 2 blocks, and we can label them conveniently as 1A, 1B, and 1C. And for this particular configuration, we find that there is no degeneracy, because in the inner code we have these 2 blocks in which we apply the usual, the for each of these blocks we apply the bit flip operators, stabilizers, and corresponding to the XX operation, we have the logical operators of the bit flip code, which is given by this, and thus we find that in fact there is no degeneracy. But again, I hasten to add that it is a particular artifact of the system that we've considered, more general systems can give rise to degeneracy. A similar exercise can also be done for the 10-1 code. So we have encountered the DFS, the stabilizer generators for that. Now the stabilizer generators for the 5-qubit code are given by equation 6.1. Again, in the QD case, we can think of them as having 5 blocks, in each of which you have 2 qubits. And we have in each of these blocks, you have the DFS stabilizers coming in. And for the outer blocks, we write them, and each of them would have an interpretation of, because of the multiplicity that we inherit from the DFS. You have 2 possibilities. So therefore, S6 would correspond to 2 into 2 into 2 into 2. So 16 possible, degenerate stabilizers. Now notice that because it's a 10-1 code, you need 10 minus 1 stabilizers. So we have all the 9 of them accounted for in equation 6.18. But S6, S7, S8, and S9, you can have 16 possible generators that do the job of S6. So that is the degeneracy. And the analogous thing can similarly be done in the DQ case. And as in the 6.1 code, here again, we find that for the particular examples we have considered, there is no degeneracy. So to summarize the various numbers, we have considered the 6.1 DQ QD code and also the 10.1 QD and DQ code. And the error types would be X and XX. So these are various errors that we encounter in each of these systems. The efficiency, because of the inflation that is provided by the the degeneracy, we get them to be 1, but we get more realistic assessment of the performance when we look at phi prime, which is the modified efficiency, which is again summarized from what we showed earlier. And again, we have the threshold, which can be computed for each of these codes. And so this is what we obtain. So to conclude this work, we study codes obtained by concatenating QECCs and DFS. And this concatenation is suitable for, it is when you have a mixture of both independent and correlated errors. And when the errors are sufficiently strongly correlated, then it is good to have the DFS as the inner code, and vice versa. If the errors are sufficiently independent, then the QECC should serve as the inner code. That is, you should have a DQ code. Now, the concatenation of QECC and DFS results in a kind of stabilizer structure that splits naturally into passive and active parts. So the active parts are those for which you determine the syndrome and then you apply the error, whereas the passive parts really leave the encoded state unchanged, invariant. So for examples, we looked at the concatenation of the 2-1 DFS with 2 types of error correcting codes. One is the 5-qubit null alarm code and the 3-qubit bit flip code. So the QD and DQ codes can be considered as generalizing the stabilizer codes to a new class of hybrid codes where we have degeneracy in both the stabilizer and in the errors. So these are various references. These were seminal papers 1, and these are some of the papers that we've looked at. And I thank you for your attention. And hope I've been able to communicate something.
Okay, so I mean, thank you, Srikanth. Now I think any questions? So Srikanth, these DFS codes are for correlated errors, is it?
They would be suitable for correlated errors because the whole idea is that the decoherence-free subspace comes from the symmetry in the noise. In other words, correlation in the noise. Like for example, if you have, let us say you have 2 qubits which have correlated dephasing, meaning to say we've looked at x6. You could equally well have phase gates that are applied to both the qubits. Then again, you will find that the 0 1 and the 1 0 state, each of them pick up the same phase, and therefore you can have your logical state as the 0 1 and the logical 1 state as the 1 0. So whenever you have these correlated errors, yeah, that's when the DFS comes into picture.
Okay,
If you
so
have
suppose you have, so suppose you have a correlation in larger number of qubits, then you will use, say, not 1 2 1 3 or something. Is it
Oh yeah, yeah, absolutely. I mean, you can have 4 qubits. I mean, yeah, for whatever. So the main idea here is that because of the symmetry, they will process a group structure, and then one can look at obtain the irreducible group, irreducible representation for them, irrep from for them, and then we can combine them to construct a projector into the DFS space. That's a way to identify the quiet corner in Hilbert space, where because of the symmetry, the evolution within that quiet corner will, it will evolve only up to a unitary.
So, but is it surprising that when you have more, I mean, when coherent errors are more probable, then your inner code will be this DFS, right? So it is not that surprising.
Oh yeah, yeah, indeed, indeed, yeah. That thing comes out really powerfully. So when you have, even in our plots, we saw that when we take in those examples, mu is equal to 0.75, and we take the uh, when we take the DQ code, that is the inner code is QECC. Actually, it is worse than not encoding.
Yeah,
Whereas a
yeah.
QD, yeah, yeah.
I
Whereas
mean,
QD,
yeah, I mean that will appear quite natural, right? Because your DFS will work better, right? When
correct, correct,
it's coherent,
absolutely,
right?
yeah, yeah. It is as expected, absolutely.
Okay. So I think everything is quite well understood here. Actually,
Oh,
some of students here may not be very familiar with this concept of DFS, and this concatenation of different these type of code.
okay.
But anyway, so I don't know if there are any questions on YouTube, etc. I don't know.
So there are no
Are there,
questions on YouTube.
are there any questions there?
There are no questions on YouTube.
No, okay, okay. There are no questions. Okay, thank you. So, okay, good, good. You should have to. So don't worry, your question may not be asked and
Hello.
Yeah, sure.
So you showed an inequality which was saturated. What does that inequality refer to? Was it the degree of degeneracy of the code? Like, what is a degenerate code?
Oh, okay. Yeah, yeah. So by a degenerate code, normally what we mean is that let's say, for example, you take a Knill-Laflamme code, you have 16 possible errors. Like you can have errors in the first or the second or the third or the fourth qubit corresponding to each of the Pauli errors. Each of them will generate a distinct syndrome, and you can detect the syndrome, and then you have the diagnostic in hand which error to apply, and therefore you can apply it, and then you eliminate the error. Now if you are familiar with something called the 9 qubit shore code, right, then yeah, there you will find that in the first block, if you have errors, z1 or z2 or z3, right, they produce the same phase flip. Okay, so you can have distinct errors which produce the same effect on the state, and of course correspond to the same syndrome. So errors which produce the same effect on the encoded state, they are called degenerate.
So are they not more difficult to correct for?
Oh,
Because
okay. Huh. Yeah,
because once you get the
absolutely.
syndrome, you wouldn't know which of the three errors occurred. For example, in this case.
Absolutely. You have raised an interesting issue. So the point about degeneracy is that it won't matter not being able to distinguish them. If you look at what degeneracy says. So, for example, in the shore code Z1, Z2, Z3, as you correctly point out that you cannot distinguish these three errors, but it also turns out that it doesn't matter because they modify the state in the same way. Now, the danger that you're pointing to comes when you have some unallowed errors. So, let's say, for example, you have a CNIL Laflam code and you have 16 errors. It's a perfect code, meaning you have 16 syndromes, that is n minus k is 4, 2 power 4 is 16, and you can have 16 errors, and those 16 errors are exhausted. Now, let's say you have an error which is Z, one error which gives rise to a particular syndrome. Let's say 1, 1, 1, minus 1. Now, if you have more than the allowed errors, let's say you have two errors, let's say you have an error in x1 and z2, right? Now, that might coincide with some other syndrome which is coming from a legit error, that is a correctable error. So, that will take us to the problem that you're talking about. So, if you exceed the allowed correctable limits of a code, then you might have errors which will start coinciding with the syndromes that correspond to certain correctable errors. So that would be a different issue. But if you're just talking about degenerate errors, then by definition, degenerate errors produce the same effect on the code. So it doesn't matter that you can't distinguish them.
Okay, okay. And like one last question, what was the inequality about? You showed that it was one. It
Oh,
was
okay, okay. Oh,
accuracy.
okay.
What was that?
So, oh, okay. Yeah. So that inequality is basically what we call as the Hamming bound. Okay. So you expect it to be for a perfect code, it will be one. That is the number of. Yeah. I'll try to go to that slide. Is it visible? The slides?
Yes.
Okay, but not maximized, right?
Yes.
Okay. I'll just go to maybe slide. You mean this? Here?
The one before this.
This one? Okay. Yeah, so in general, what we are, so maybe this?
Yeah, this one, this one. Yeah, sorry, this one.
Yeah, yeah. So, yeah, so the Hamming bound essentially is sometimes called the sphere packing bound, which says that n minus k, right? It is like the real estate that is available with you to keep track of all the errors. So you want n minus k to be larger than the, sufficiently, that is 2 power n minus k must be larger than the number of correctable errors. That is, each of the correctable errors can be identified. So that is what this basically says. It's a sort of a crude bound which says that you should have enough uh, correction real estate that you can identify and eliminate all the errors. So that idea, therefore, you can say that that point can be expressed in equation 6.10 as an efficiency, as what we call a Hamming efficiency. So you can say that every code should have this phi efficiency at most being 1. And if you have it exactly as 1, then you have what is called as a perfect code. That is a code that saturates the Hamming bound. That is, the all the syndromes are being exhausted for the corresponding to the errors. And so when we evaluate it, actually we find that it is 1. And even though it doesn't have, one can do the counting and find, one can show that certain syndromes are not used. So it's not a perfect code, but it's giving us 1 because of this degeneracy. Meaning to say that a given syndrome, right, it's you have a number of degenerate errors. So as a result, this thing is getting inflated and it's giving, 1. So the number of syndromes that are actually being used will, for that, it's better to look at all the non-degenerate elements, and that is what the modified efficiency does. So that gives us a better sort of check on better estimate or better assessment of the performance in terms of the Hamming bound when you're talking about degenerate codes, where the degeneracy can artificially appear, boost the performance.
Okay, thank you.
Feel free to ask, even if you think a question may not be making. Any more courageous person? Okay. So Srikanth, I think there are no more questions. So thank you very much. So
Yeah, thank you.
our students have been exposed to a new area, which I think they would like to explore more and learn more. Okay?
Thank you so much, Pankaj, and thank you to all of you for your kind attention. And I just hope I've been able to communicate and not bore you all. Yeah,
No, it is always good to be exposed to a new area. Okay. So thank you very much.
yeah. Thank you. Thank you.